this section, we're going to look at some application problems involving exponents and logarithms so that you can kind of see how exponential equations factor into the real world. Before we talk about some applications of exponential functions, let's compare linear and exponential functions. They're very similar in some respects. Linear equation, we have our slope-intercept form, y equals mx plus b. This gives us two pieces of information. The first is the slope. This is a constant that is added to each y value as x increases by 1. We also have the y-intercept, or the initial value, the initial y value, when x is 0, which is our b. When we talk about exponential functions, we have two concepts that are almost the same. Instead of having a slope, we have something called a base multiplier. This is the b inside the equation. It is the one that has the exponent attached to it. Like the slope that we have, the slope is added to each y value. The base multiplier is a constant that is multiplied to each y value. We also have a y-intercept, or an initial value. In this function, or this equation, it's going to be the a. It's going to be the one that does not have the exponent. We're going to be translating into some exponential functions. So we do want to kind of know where these numbers are going to go. All right, so these problems come from the final review. I figured that would be the easiest thing to do for you guys. The first one, we have, suppose the newest version of your favorite smartphone comes out today, and assume that a total of 30 people go to your local cell phone dealer to purchase this phone today, and that each day the total number of people who purchase the smartphone doubles. Let S of t represent the number of people who have purchased the smartphone at t days since today. So we have our function S of t equals a times b raised to the t. And so we want to go ahead and plug in some of these values. What is the base multiplier? Well, the base multiplier says the total number of people who purchase the smartphone doubles. Doubles means multiply by 2, so that is our base multiplier. That will be our b. A, I said, was the initial amount. So it says that the total number of people who bought the phone today was 30. So that's going to go in for A. So this is our answer for part A. We have our function S of t equals 30 times 2 raised to the t. For part B, it says, according to S of t, how many people have purchased the smartphone 7 days from today? Notice t represents the days since today. So for part B, we want to calculate S of 7. So if we plug in 7, we get 30 times 2 raised to the 7th. From here we want to use order of operations in order to simplify this. So I'm going to start with my exponents. 2 to the 7th is 128. And if we multiply 30 times 128, we get 3840 people have purchased the smartphone. And we're done. Let's look at one more example that's similar to this. We have, suppose a flu epidemic breaks out in all our Math 120 courses at school. Assume a total of 9 people have the flu as of today, and that each day the total number of people who have the flu triples. Let f of t represent the number of people who have the flu at t days since today. First thing we want to do is find an equation. So we have our s of t, or what is it, f of t? I guess for flu, equals a times b raised to the t. So what is our base multiplier? Well, the word that we have that shows multiplying is the word triples. Triples means that each day it multiplies by 3. So I'm going to put that in for my b. What is our initial value? It says that 9 people have the flu as of today, and so that is my initial value. And that is our equation. For part B, it says how many people at school will have the flu 4 days from today. So we want to plug in 4 for t, that is our time. So we get f of 4 equals 9 times 3 to the 4th. Again, we go ahead and evaluate this. We get 9 times 3 to the 4th is 81. If we multiply 9 times 81, we get 729 students. That's a lot. We won't go into the fact that we don't even have 729 students in the Math 120 classes total. Let's just pretend that it's possible. But one of the things to note here is when we talk about exponential functions is they grow quickly. They grow very quickly, very fast. Okay, so hopefully we kind of see where these numbers come from. So let's do some other things with exponential equations. All right, the next one we have, it says statistics indicate that the world population since World War II has been growing exponentially. If we assume exponential growth, the world population can be modeled by the following function, where p of t is the world population in billions, and t is the time in years since 1995. So make sure that we pay particular attention to that statement. We want to start by estimating the world population in 2015. So the first thing that we need to do is go ahead and figure out what is 2015 in terms of 1975. For A, start off by subtracting. (2015) is 40 years after 1975. We can go ahead and now plug that into our function. So we get p of 40 equals 4 times 1.019 raised to the 40th. We want to go ahead and start by applying our exponent. Using our calculator, we get 1.019 raised to the 40th. Remember that you want to use the caret key on your calculator. I got 2.123. And if we multiply that by 4, we get 8.492. It does say that our population is in billions. So we have the population will be 8.492 billion in 2015. Let me make that a little clearer. Okay. Okay, so we have that. For part B, we want to go ahead and figure out when the population will reach 10 billion. So we are being asked when, meaning we need to find the t value. That means that 10 is our population. We're going to say 10 equals 4 times 1.019 raised to the t. Okay, so we want to solve for t. The first thing I want to do is get the exponential by itself. So I want to divide by 4. If we divide 10 by 4, I get 2.5. And I'm going to go ahead and just work with decimals because it's a little easier in my calculator. Now we do have an exponential equation here. So if you recall from 2 presentations ago, the easiest way to solve a exponential is to take the logarithm of both sides. So if I take the log of both sides, I get log of 2.5 equals, I can move my t down to the front, and we get t times log of 1.019. From there, we want to divide by log of 1.019 to both sides. And then use our calculator. When we put this in our calculator, remember that we want log of 2.5, close our parentheses, divided by log 1.019, close our parentheses. Go ahead and take a minute and see what you get on this. And the answer that I get is 49. I'm going to go with 49 because up here it did say round to the nearest year. I got 48.68, etc., etc., etc. Now, when we do this, it says when, so I do want to add this to 1975. So the population will reach 10 billion in 2024. And we're done. Okay, so that takes care of A and B. For C, we have, according to this model, what was the world population in 1975? And so remember that 1975, that is year 0. So the question is, what is the y-intercept? Well, remember that when we talked about how to break up or how to create these equations, remember that we said that the number in the front, the very front, the one that does not have the exponent, is our y-intercept. And so this one is going to be 4. So the population in 1975 was 4 billion. Okay, for part D. Part D asks, according to the model, by what percent is the world population growing each year? Okay, so we didn't really have a lot of time to go over this. Okay, at all. So I'm going to show you kind of how this works without going into any other examples. When we talk about our base multiplier, the base multiplier here is 1.019. This here is a percent. If I wrote this as a percent, this is 101.9%. We have that it is a percentage over 100 because it is a growth, which means that each year we have more than 100% than we did the previous year. So what we want to do in order to figure out the percentage of growth is I'm going to subtract off 100 to get 1.9. The population is growing at a rate of 1.9% per year. That is how much extra is being added on each year. Okay, so that takes care of this problem. Let's look at another one. So we have a function f of t. It says that suppose $2,000 is deposited into an account where the interest is compounded annually. The situation is modeled by the function 2,000 times 1.052 raised to the t, where f of t represents the value in dollars of the account at t years after depositing the $2,000. Problem A, we have in how many years will the money in the account double? So we're being asked how many years, which means we're looking for a t value. And if the money in the account doubles, how much money is going to be in there? Well, we multiply 2,000 times 2, and we get 4,000. And so this is the function or the equation that we want to solve. Just like on the previous one, we want to start by isolating the exponential. So we're going to divide both sides by 2,000. We get 2 equals 1.052 raised to the t. In order to get t out of the exponent, or to get rid of the exponential, we want to take the log of both sides. So we get log of 2 equals, I'm going to move my t down to the front, so we get t log 1.052. This is multiplication, so in order to get t by itself, I want to divide by the logarithm, and now if we go ahead and solve this, we have log of 2 divided by log of 1.052. And the answer that I get, in how many years will the money in the account double? I get in 14 years. I am rounding up because I got 13.673. Okay, that takes care of A. Okay, for part B, it says, according to the model, how much money will the account have in 10 years? So for B, we're wanting to know the amount of money, so we have f of 10. 10 is a x value, or a t value. So we're looking for when t is equal to 10. So we get 2,000 times 1.052 raised to the 10th power. Okay, so if we go ahead and plug this into our calculator, I get 1.052 raised to the 10th. I get approximately 1.66. There is more decimals there, and you do need to keep them because as soon as we multiply by 2,000, we should get $3,320. And I'm not sure exactly what it wants us to round to, so I'm going to leave it at dollars. And we're done with that one. Okay, for part C, we have what is the earning interest rate? So again, we're only going to look at our base multiplier. We have 1.052. If I wrote this as a percentage, this is 105.2%. Now keep in mind that we're just putting money into this account. We aren't taking anything out. So what we want to do is, again, subtract off our 100. That was the original amount, or the original percentage. And we get 5.2%. So the account is, the earning interest rate is 5.2% per year. Alright, that takes care of our application problems. Hopefully these made sense. Any questions that you have over these, please bring to the review session on Monday if you need to go over them in a little bit more detail.